previously seen that first ionization results in an atom losing an electron, and it creates what we call a monopositive ion. So this is an ion with a +1 charge. So this X could be any element, and we end up with a +1 charge. That's a monopositive ion. And then we saw that if the conditions are right, if you provide enough energy, that monopositive ion can lose a second electron, and then that dipositive ion can lose a third electron, and so on. And you can keep removing electrons, and this will give us what we call the second ionization energy, the third ionization energy, etc. So what we're going to look at here in the next element is we're going to take, in the next section, we're going to take an example of an element, and that element is going to be potassium. And we're going to look at what happens as we remove more and more electrons from it. But before we do, we need to remind ourselves of a couple of things. So what I want you to do is I want you to do these questions 3, 4, 6, and 3, 4, 7. So go ahead, pause the video, write down the SPD electron configuration for potassium. And when you're finished doing that, draw the Bohr atom of potassium. So this is an atom with the energy levels shown as circles with the electrons in it. So pause the video and do that now. Okay, so you should only be playing if you've done those two questions. It's really important to remind ourselves of these two things before we begin. So let's go ahead and do that. So potassium has a symbol K. Potassium has, I believe, 19 electrons, but I'm just going to check. Sorry. Yeah, potassium has 19 electrons because it has an atomic number of 19. So we're going to go ahead and so we've got 19 electrons. We're going to go ahead and write the SPD configuration. You should have done this. 1s2, 2s2, 2p6, 3s2, 3p6. That's 18 electrons, and then 4s1. Okay, so that gives us 19 electrons. And then you have to draw a Bohr atom or a Bohr model of it. Okay, so what we want to do is we want to put the nucleus in the middle, and then we draw the energy levels as circles, and we're going to fill it in with electrons. So here's the first 2 electrons. Then we've got a second energy level, and here are the next 8. 1, 2, 3, 4, 5, 6, 7, 8. There's the next 8. That's 10 altogether. I'm going to draw a third energy level, n equal to 3. And here are 8 more. 1, 2, 3, 4, 5, 6, 7, and 8. And then lastly, we've got 1 more electron, and it goes in the 4th energy level like this. And there it is there, at 1 electron in the 4th shell. Okay, so that represents for us the atom of potassium. So let's look at this graph now. Okay, so we're going to study this graph. What does this graph show? Well, first of all, the title says that these are the ionization energies for potassium. So we're looking at potassium. And let's look at what the graph shows. On the x-axis here is the number of electrons that have been removed. So obviously it starts at 0, and as we go from left to right, the number of electrons that have been removed is increasing. And on the y-axis, we're showing ionization energy, i.e. ionization energy measured in kilojoules per mole. And obviously, as we move up the axis, the amount of energy required is increasing. Okay, so let's look at each of these data points. Each of these data points shows an electron being removed. Okay, so this here shows us the first electron being removed. So as you can see, that is quite a low amount of energy. It's the lowest value out of all of these values. We say overall, it seems to be decreasing. It's getting harder to remove the electrons as we remove more and more. Which electron would this be? If we go over and we take a look at the atom, well, the first electron is going to be the most loosely bound one. It's going to be this one. So this is going to be the one that's lost. And as you can see for potassium, that's the lowest energy required. And that's because that one is attached quite loosely. It doesn't take much energy to remove that. So let's go ahead and do that now. Let's show what would happen. Okay, well, if we remove that electron, then essentially that electron is gone. And now that energy level is also gone. We don't have any electrons in the n equal to 4 energy level anymore. And so therefore we don't need to draw it anymore because it's empty. So what's left behind now is this obviously K+1 ion. It's now got 1 extra proton than it does electron. But now what we see is we now have this full octet, or this atom is now what we call it. It has It's satisfying the octet rule all of a sudden. It's satisfying the octet rule because it's got 8 electrons in its outer energy level. So its outer energy level is now this n equal to 3, 1, and it's full. It's got 8 electrons here. So we would see then that if we were to try and remove a second electron, say this one here, if we were to try and take that one away, well, now we're taking it from a full main energy level. We're taking it from a full 2p sublevel or a full main energy level, and this is going to be much harder than it was to remove the first one. And that's why we see this big jump here. So to remove between the first and the second one is much harder, requires a lot more energy. So that's why we have this big jump here. This is a large jump because this second electron is being removed from a full main energy level, or from an atom that has a stable octet, if you like. Okay. What we then see, though, is we then see pretty much this very steady or flat increase for the next 1, 2, 3, 4, 5, 6, 7. Okay, is that, just check that again. 1, 2, 3, 4, 5, 6, 7. Okay, so obviously this jump from here to here shows us removing this first electron. Oops, sorry. Shows us removing this first one. Okay. That was quite hard to do. That's why there was this big jump. But now to remove this next 1, 2, 3. Oh, sorry. Where are we at? Okay, so 1, 2, 3, 4, 5, 6, 7. To remove those 7, it doesn't take too much energy, which is why it's pretty much, all of these are pretty much the same value. It's just a slightly steady increase, sorry. And then what we see is, well, to remove this 10th one would be one of these ones. And again, I'm taking this 10th one from a full outer energy level. Again, this is currently in this state here, it's satisfying the octet rule because it's got a full outer main energy level. So this here is where we see another quite a big jump in energy values. Okay, and what do we notice is that 7 more later, there is another jump. Okay, and that would be when we have removed that outer shell again, and now we're taking one of these electrons from the full first shell. Okay, that's that one there. Okay, when we're trying to take that one, there's a big jump again, and then obviously that there is now, that will be all of the electrons removed. There's no electrons at all here now. So we've gone through the process of removing all the electrons, and what we see is this massive big jump. Okay, or what we would call here, here, and here, we see what we would call a significant jump. And it happens every 8th electron removed, every 8th electron. And the reason for this is that we're now taken from another energy level, if you like. We're removing from a full energy level. Now, this is another piece of evidence that energy levels exist. Because if they didn't, and the electrons were just randomly anywhere in around the atom, then we wouldn't see these patterns. So this is another piece of evidence that energy levels exist. And you're often asked that question, what are some pieces of evidence that energy levels exist? And I suppose that this here is one of them, the fact that you see significant jumps in ionization energies after every 8th electron removed. And the other one that we saw already was emission spectra. So when Bohr used emission spectra, and the fact that emission spectra have specific frequencies, then that's evidence that electrons can only be in certain places. They can only have certain energy values. And that's why you only get certain lines on emission spectra. So this is the 2 pieces of evidence, okay, 2 pieces of evidence that energy levels exist. The emission spectra is 1, okay, and then these significant jumps in first ionization energies, every 8th electron removed, that is another piece of evidence. So just wanted to show you that scientists don't just rely on one piece of evidence, they try and collect together as much evidence as they can. So this was another piece of evidence that really confirmed for scientists that the model of the atom with their energy levels is the correct one. Okay, so I'm just going to quickly read through, make sure I haven't forgot to tell you anything here. Sorry. Okay, so what does the graph show? The graph shows successive ionization energies for potassium. So successive just means one after the other. So removing the next one and the next one and the next one. So that's what we've shown. The general trend is that the energy required to remove an electron increases with each ionization. Why does it increase with each ionization? Well, remember, for every electron you remove, okay, for every electron you remove, so say the first electron removed is being taken and it's creating, so we've got X giving you X plus 1 plus that 1 electron. Okay, that's first ionization energy. Second ionization energy is coming from the X plus 1 ion. So this essentially has a bigger effective nuclear charge because there's extra protons. So to turn from X plus 1 to X plus 2, you have to remove an electron away from an already positively charged atom. So that's why we get this general increase. Okay. So, however, there are some interesting observations. It's not just one straight line. The energy required to remove the first electron is relatively low. Okay, as we saw here, low. This is because the electron is in the n equal to 4 energy level, so it is far from the nucleus and the screening effect is large. There is a distinctly large spike or a jump for the second ionization energy, this bit here, okay, and meaning that this electron is more difficult to remove. That's why there's this big jump. This is because the electron has been removed from a full n equal to 3 energy level, which is very stable electron configuration. Note that there are 8 similar-ish ionization energy values before another spike is seen, going to another full energy level, which is closer to the nucleus. So we see this other spike 8 electrons later. Note, so yeah, the jumps in ionization energy are a major piece of evidence used to prove that energy levels really do exist. Okay, so again, it might be a good idea for you to make note of the 2 pieces of evidence that support the existence of energy levels. All right, so you're given some information here before we do some questions. It says the first, second, and third ionization energies, this should say, energies of magnesium, the element magnesium, are, so 731, well, this is the first ionization energy because it's the first value. 1450, this is the second ionization energy because it's the second value. And then look at the difference here. I just want to point this out to you. 737, 1450, and then whoa, 7731. So a massive jump to the third ionization energy. So I wanted to point that out to you before you begin to do the next set of questions. So what I wanted to do is I wanted to complete these questions, okay, and we'll go through them in class the next day. If you need the booklet to go back through the information, go ahead and find the OneNote or find the booklet to go back over if you need to revise. You may need to go up and look at that graph again, so do that, and I'll see you the next day in class.